of solutions, and in this particular case we're going to work on the freezing point and the boiling point. Okay, so we're going to work our problems. Now these are simple equations. They pretty much look the same. We have the change in freezing point, and here we have the change in boiling point. And they would be the same except for our constants are different. This is our KB and this is our KF. Remember, I is the Van Hoff factor, which is the number of particles particles dissociated to. And we're using our concentration in molality here. Molality. Okay, so these are real simple. We're going to use them over and over. The trick is boiling point and freezing points. Now this one gives you a chart with some species. This is the one that I like to use. It's kind of got them all. Notice that we have all kinds of species. The ones that I want you to make note of is water. I will give you the KFs and the KBs, but I assume that you know that the freezing point of water is 0 degrees Celsius and the boiling point of water is 100 degrees Celsius. Now, on the test, we may not be using water. We can use chloroform, benzene, acetic acid, any variety of things, and we will work a problem with that. But we may also work one with water. Okay? So, we have a researcher preparing a new compound, uses freezing point depression. Now we got a lot of words here. These are word problems. So I'm going to pull out what I think I might need. So I've got the compound, which is my unknown, which is 1.50 grams. We're dissolving it in cyclohexane. So our solvent is 75.0 grams of cyclohexane. Okay, we're told that cyclohexane pure has a freezing point of 6.54 degrees C. And the K sub F, which is the freezing point depression constant, is 20 degrees C per molar. That's what kilogram per mole minus 1 is. Freezing point of the solution, so our solution freezing point is equal to 2.70, and we want the molar mass. Well, that tells me if it's a molar mass, then we have delta T sub F is equal to I K sub F times the molar. And if it's molecular, then I is equal to 1. So what we need is the change in freezing point. Well, delta T sub F is equal to T final minus T initial. We always want it to be positive. So we get 6.54 minus 2.70, which gives us 3.84 degrees C. Okay? So what we want to do is go over here and we'll say 3.84 degrees C, 84, is equal to K sub F, which is 20.0 degrees C per molar. Okay, so if we multiply both sides by the molality, so the molality comes out equal to 20.0 degrees C divided by 3.84 degrees C. I just flipped that upside down. Oh, that was my problem. I need the molality there. So, again, helping erase things. This is combined. So this is part of my constant. So my molality is 3.84 degrees C divided by 20.0 degrees C per molar, which means I get a value of 0.192, and that's moles per 1 kilogram of solvent. So if we go back over here and look, if we know that our solvent is 75 grams, that's 0.75 kilograms. So we'd multiply it by 0.075 kilograms. So if our kilograms of solvent cancels, then we know that our unknown is 0.0144 moles in this compound. Now, molecular weight is equal to grams per mole, right? So if we look at it, wait a minute, we have the grams of the unknown. Now we have the moles of the unknown. So if we divide grams divided by moles, we end up with 104.1667 grams per mole. So this is our molecular weight of our unknown. So the math on this is actually kind of simple, and I like it because to me it's relatively simple, even if you're not using water. So let's do another one. So the boiling point of carbon tetrachloride, okay, here we go again. So we're going to use carbon tetrachloride as our solvent. So it's 15.0 grams, which means it's going to be 0.015 kilograms of our carbon tetrachloride. We're told that the boiling point is equal to 76.75 degrees C. We're told that the Kb is equal to 5.03 degrees C per mole. We're told that our drug, sulfanilamide, is 0.98 grams. And the solution has a boiling point equal to 78.70 degrees C. So we know that delta T sub B is equal to I K sub B molar. And I is going to be equal to 1 because, again, this is a molecular compound. So if we look at it, our delta T is going to be equal to 78.70 minus 76.75, which is equal to a whopping 1.95 degrees C, which is actually a lot. So if we set it up as delta T sub B is equal to 1 times K sub F times the molality. That means it's 1.95 is equal to, what's the K sub B? 5.03 degrees C per mole times our molality. Our molality then is going to be equal to 1.95 degrees C divided by 5.03 degrees C, which is equal to 0.38767. Now remember that's molality, which is moles per 1 kilogram of solvent. We know that we are given 0.015 kilograms of solvent. So that tells us that we are left with 0.0058151 moles of our unknown. And our unknown happens to be the drug here. Molecular weight, remember, is grams per mole. So that means it's 0.98 grams divided by 0.0058151 moles, which gives us 168.52 grams per mole. All right, so the previous problem we had about 104. This one's 168. Some proteins are done this way, and proteins are massive. So as long as it's a molecular compound, if it comes out kind of small or kind of large and you've done the math right, don't sweat the small stuff because it may very well be correct. So on this next one, again, we're still dealing with an unknown sample with the molar mass. So I is still going to be equal to 1 here. And our solvent is paraxylene. So we know that the freezing point is equal to 13.26. Kf is equal to 4.3 degrees C. Our unknown is 0.9981 grams. We're in 25.0 grams of paraxylene, which means that's 0.025 kilograms, and we'll need it later. The freezing point of the solution is equal to 12.47 degrees C, and we want the molecular weight is our unknown. Okay, so again, delta T sub F is equal to I K sub F times the molality. So we can rearrange that, but the first thing we're going to need is delta T sub F, which is equal to 13.26 minus 12.47, which comes out to be 0.79 degrees C. Now, some of you are like, delta is final minus initial. Yes, it is. But in the case of freezing point depression, our final is going to be the solution, and so we'll end up with a negative value for temperature. And when we put it into the equation, we need the positive. So here we go. So delta T sub F is equal to K sub F times the molality. So the molality is going to be equal to delta T sub F over K sub F, which is equal to 0.79 degrees C divided by 4.3 degrees C per molal. And so our molality comes out equal to 0.18372 moles per 1 kilogram, because remember that's molal, and we know we have put it in 0.025 kilograms of solvent. So this gives us a moles of 0.004593 moles. 0.4593 moles. Molecular weight is grams per mole. So it's going to be 0.998 grams divided by 0.004593 moles. It gives us a molecular weight of 217.3078 grams per mole. So with these values, this is really easy to do. When we do the freezing point depression in the lab, I'm going to be giving you the data. If you're actually in lab, you would produce the data yourself, but I'll probably be giving you the data in the I will be giving you the data in the summer semester. So you're going to basically use this to determine the mass of your unknown. Okay, I want to work one more problem because I want to work it the other way. And by the other way, I mean I want to look at it with respect to the I factor. So when you look at the formula, is delta T is equal to I K sub F molality. So up to this point, when we were doing our unknowns, we were doing all molecular compounds. So I was equal to 1, except this is a salt. So it's going to dissociate into magnesium 2+ plus 2 chlorides. Well, if I could write chlorides. So basically, we're going to end up with 3 times the particles. So when we look at this, we're trying to find the original concentration, so we actually want the molality. So we're doing this in an aqueous solution. That means aqueous is water. So we know that the freezing point of water is equal to 0 degrees C, and our K sub F is given. So we'll know that the delta T here is going to be 2.67 degrees C. Our I on this one will not be 0, or excuse me, 1 like we've been doing. It'll be 3. Our Kf is 1.86 degrees C per mole. And then we're going to solve for the molality. Okay, so the molality is going to be equal to 2.67 degrees C divided by 3 divided by 186 degrees C per mole. And that means that it'll come out to be 0.47849. So this is the concentration of this particular solution. Now, another way you could have done it is you could have done it in reverse. So another way is just to do it and then look at the number of particles. So in this case, it's still 2.7 degrees C. You still have 1.86 degrees C per mole. But now you're looking at the molality of the total solution. So in this case, your molality comes out equal to 1.4355 mole. But you know that you have 3 particles. So you'll end up with 0.47849 molar. So it doesn't matter which way you do it, as long as you remember to take into account the fact that this is not a molecular compound and it is going to dissociate into a variety of particles, and in this case the number of particles is 3.